All right, let's get started now. Once again, thank you everyone for joining today. Today we're going to be talking about GFRP concrete design as well as software for analysis and design of GFRP reinforced concrete. I'm joined today by Dr. Ali Reza Assadian from MST Bars. He's a technical director of MST Bar, and he's going to be giving an introduction to GFRP concrete, its applications, the design codes being used, and more. And after that, you're going to hear from me again. My name is Matthew Sarr. For those of you that aren't familiar with me, I work for Altair. I am a part of the global technical team. I manage the AEC global technical team, and I'm going to be presenting some of the design software that Altair has developed with the help of MST Bar for GFRP Reinforced Concrete. We're going to have a Q&A session at the end of this presentation as well, so you're more than welcome to type in your questions into the Q&A field. We'll do our best to respond to whatever we can during the presentation, but if there is a lot of questions, we might not necessarily have the bandwidth to cover them all, so we'll try to cover those in the coming days via email. So at this point, I would like to open up the floor for Dr. Ali Reza Assadian. Ali Reza, do you mind just sharing your screen and we can get started with your portion of the presentation?
Yeah, sure, Matthew. Do you see my screen?
Yes, I can see it now. Thank you.
So thank you, Matthew, for the introduction. Hello, everyone. My name is Ali Reza Assadian. I am the technical director of MST Rebar. It's a great pleasure to be here, and I would like to thank Altair for inviting me to be part of this webinar. So, as Matthew mentioned, I will be doing the first part of this webinar. And in this presentation, I will first give you a brief introduction about GFRP bars. I'll talk about standards available for material specification of GFRP rebars. Then I will talk briefly about the benefits of GFRP rebars when you look at it from the long-term durability. I will touch base on the carbon emission benefits of using GFRP rebars in construction project. Then I will show a few pictures of some of the field applications where we used MST bar over past decades. And finally, I will touch base on the basics of design of GFRP reinforced concrete for you to get familiar with the design. So as you may have noticed in your everyday commute, our infrastructure is suffering from corrosion of steel reinforcement. And corrosion of steel reinforcement happens by penetration of fluoride into concrete. So corrosion can form the volume expansion of the rebar and can induce more cracking and cover spalling and exposure of internal reinforcement to aggressive environmental conditions. And also very important to know that corrosion is accelerated by carbonation of concrete that lowers the pH environment of the rebar, and this carbonation happens over the lifespan of the structure. Engineers obviously are aware of the issue of corrosion. They take additional measures to mitigate corrosion of steel reinforcement in steel reinforced concrete structures. And those measures include the use of corrosion inhibitor admixtures, use of alternative reinforcing materials such as epoxy-coated galvanized steel or stainless steel rebar, use of sealer and membrane and concrete surface, or providing additional cover, and so on and so forth. It is, however, very important to know that those measures are, first of all, costly. They will add to the initial cost of the project, and they can only delay the issue of corrosion. They will not eliminate the issue of corrosion. Corrosion can also result in degradation of the strength of a structure over time, which can result in catastrophic failures. For example, this is a picture of a parking garage that collapsed back in 2008 in Canada. And the collapse of this parking garage unfortunately resulted in one casualty. And the main reason for the collapse of this parking garage was the lack of regular maintenance to prevent the corrosive effect from de-icing salts. And that is why we believe MST Bar offers a solution that not only addresses the corrosion issue in reinforced concrete structure, but also provides several additional benefits to construction project, which I will cover during this presentation. Now, what is a GFRP bar made of? GFRP, or glass fiber reinforced polymer bar, is a composite material that is made of fiber and resin. There are many types of fibers excuse me, available in the market, but what is of interest from structural engineering applications and also from an economical and durability perspective is glass fiber. And we use the latest generation of glass fiber called ECR glass fiber. And the resin that showed a very good performance and durability for construction application is vinyl ester that we used. Worth noting here is that in a cross section of MST bar, there is around 80 to 85% continuous fibers, and the remainder of 15 to 20% is vinyl ester resin. Now, what are the mechanical and physical properties of GFRP bars, and how does it compare to conventional black steel rebar? GFRP bars have higher tensile strengths. Their tensile strength ranges from 1,200 MPa to 1,500 MPa, or somewhere around 180 KSI to 200 KSI. However, they have less or lower modulus of elasticity. Material is elastic up to failure. However, the elements made with GFRP bars will show very good deformability, and I will talk about deformability later in my presentation. GFRP bars are very lightweight. They weigh only quarter of a steel rebar. This will help a lot to ease the construction, to speed up the construction, and to also to reduce the transportation cost. Some GFRP bars, including MST bar, has a very high bond strain that exceeds the bond strength of a steel rebar to concrete. GFRP bars are non-conductive both thermally and electrically, so they have very low thermal and electrical conductivity, and there is no interference with wireless communication or magnetic fields when you use GFRP rebar. That's another main benefit of using GFRP bars. And also, obviously, as I mentioned earlier, one of the main features is that the material is corrosion resistant. Just briefly about MST rebar and who we are. We are one of the largest GFRP manufacturers in the world. We have 300,000 square feet plant in Toronto, and we have another plant in the US. The material is developed and manufactured in North America. We do all our research and development either in Canada or in the US. We export our rebar all around the world. To date, we sold over 1 billion linear feet of the rebar and completed over 18,000 projects. And we have currently the production capacity exceeding 400 miles or 650 kilometers a day of the rebar. So we produce MST bar or GFRP bars in different sizes, geometries, and shapes. You see a few examples here. What you see on top of this slide is our straight bar, and as you can see, MST bar has a very unique surface deformation called integral rib, and that's why MST bar has a very good mechanical bonding to concrete. Also, you see in this slide some of our bent shapes, and literally we have no limitation when it comes to production of bent bars, and we can support any sizes, any geometries of GFRP bars. So following the slides, I will briefly talk about available standards for material specification of GFRP bars. It is very important to know that not all the GFRP bars that are available in marketplace can be used in construction applications. And so GFRP bars must meet the requirements of ASTM D7957 in the US, and in Canada, we have another standard that is more stringent than ASTM D7957 called CSA S807. As some ministries of transportation in Canada and departments of transportation in the US, they have their own material specification requirements that the manufacturer needs to comply with in order for their product to be eligible to be used in construction applications. Now, what are the requirements of all those standards? Based on those standards, physical, mechanical, and durability properties of GFRP bars needs to be checked through third-party testing. There is a long list of testing that the manufacturer needs to perform. You see here in this slide the name of few of those tests, and many of those tests that you see in this slide we actually perform on a daily basis in our plant in order to ensure that our rebar continues to meet the requirements of those standards. You see a few pictures of some of the tests that we have done as a part of all the quality control and quality assurance at MST bar. So following the slide, I will touch briefly about the benefits of long-term durability of GFRP bars. There are two main types of durability tests for GFRP reinforced concrete. First, we have what's called accelerated aging tests, which are performed in controlled lab environment. In these tests, the bar are exposed to very harsh and I would say exaggerated condition to speed up any potential degradation of the rebar. And this allows us to observe long-term durability in a relatively short period of time. The standards in CSA 807 and also in ASTM 7957 require many of these tests to essentially ensure GFRP bars can withstand tough real-world conditions over time. And especially those, all of those tests are exposing GFRP bars to very harsh alkali environments. And we have conducted these tests extensively at MST Bar, and actually MST Bar surpasses the standard requirements, showing very good sort of long-term durability of the material. Beyond laboratory testing, GFRP's performance has also been validated through numerous real-world case studies. So in this slide, you can see a few examples of these studies. And actually, all of these studies show minimal or even no degradation in the integrity of GFRP bars, even after many years or 2-3 decades of real-world loading conditions. What is also important to note here is that many of these projects use the very first generation of GFRP bars that were manufactured in 1990s, and obviously those GFRP bars has much less advanced properties and durability properties compared to what we produce today, and due to advancement in technology and material, what we produce today has far superior durability properties compared to the GFRP bars that were used in those case studies. So in the following slide, I would like to emphasize on the benefits of using GFRP rebars from the environmental impact perspective, and show how using MST bar can help the construction industry to move towards using greener solutions. So as I mentioned earlier, GFRP bars are lightweight. They weigh only a quarter of black steel rebar. This will translate into less CO2 emission from transportation of the rebar to the job site. Concrete structures reinforced with GFRP bars will have longer lives, so less demolishing of existing structures, less energy to use to recycle those demolished structures, less concrete to use to build new ones to replace those structures, and this all will result in less CO2 emissions. GFRP bars are better thermal isolators, so this means that there will be less energy loss in buildings made with GFRP reinforced concrete. Also, interesting and important to mention here is that production of MST bar requires less energy compared to conventional black steel rebar. We have an EPD showing much lower carbon emission compared to black steel rebar. Also, very important to know that with GFRP bars, there is no need for additional cover or concrete cover to prevent corrosion. So that this means we can use less concrete, which can obviously directly reduce the amount of carbon emissions. Another very interesting point to mention is that chloride is not a durability concern for GFRP reinforced concrete, and this will bring a lot of opportunities to construction industry. Now, the concrete can be made of seawater and sea sand, obviously if the project has access to those materials, and there are many research studies on this subject. And also there is no need to use fresh water to make to cure concrete as well. So following the slide, I will show you a few examples of projects that we have completed with MST bar over past decade. And so the use of FRP material in construction began back in 1990s or late 1980s. But in many of those early bridges, FRP bars were primarily used as a secondary reinforcement, for example, in top mat of a bridge deck. over time, as engineers and owners observed the long-term benefit of GFRP, their confidence in the material grew. And now, 3 decades later, we reached the point where entire bridges are being reinforced with GFRP bars and with MST bar, for example. These are pictures of a bridge in Highway 11 in Canada, in Ontario, that is entirely reinforced with MST bar. Another bridge deck example in Nova Scotia with MST bar. This is a picture of CIP bridge deck in Ohio. Again, was reinforced with MST bar. Another interesting application is in caissons for soft iron tunneling application. And you see a few pictures here. Another example of caissons in Ontario. Deep foundation, another area where GFRP bars are being used, and they can provide a lot of benefits to those applications. Precast concrete culverts, underground structures, another example. These are precast sea highs in coastal areas that corrosion is an issue as well. So it was a very interesting project. Those sea hives are all 3D printed, and we had to meet very tight tolerances when we were producing the bent part for this project, and we successfully finished and completed this project without any issues or delays in construction. Another example of coastal construction, Port Killington in Ohio, 1.2 miles of port was reinforced with MST bar. Seawalls, another example that GFRP bars are provide a benefit in terms of durability in those applications. Again, we have done with MST bar miles of seawalls, and these are a few pictures from seawalls in Florida. You see a few examples here. Residential, you see a few pictures of ICF houses with MST bar, and we have done also cast in place residential buildings with MST bar. You see a few examples here. Industrial buildings, again, you see a few examples here. These are in Washington. An example here. Agricultural structures, another great example. So these are storage tanks. Those tanks are to store animal waste, very aggressive and corrosive environment for internal reinforcement. And this storage tank is in Saskatchewan, and again, a lot of benefits to the owners because of the durability of material. GFRP bars are also being used for repair and rehabilitation of existing structure. Those are pictures of Panama's main corridor bridge that was repaired with MST bar. So following this, I would like to briefly talk about design of GFRP reinforced concrete and point out some the differences between the GFRP reinforced concrete design and steel reinforced concrete design. So in terms of available codes and standards for design of GFRP reinforced concrete, in the US there is ACI code. It's called ACI code 440.11-22. This is a building code requirement for a structural concrete reinforced with GFRP. It's ACI 440.11 is what's called a sister code to ACI 318, which means that the chapter numbering, section numbering, and code language is very similar to ACI 318. Also, when it comes to the design of the highway bridges, there is second edition of AASHTO LRFD bridge design guide, a specification for GFRP reinforced concrete. In Canada, we have a standard called CSAS 806. This is for design and construction of building structure with fiber reinforced polymer. And also there is another standard or chapter 16 of Canadian Highway Bridge Design Code covers the design of highway bridges with GFRP bars. When it comes to the procedure for design with GFRP bars, the procedure for design is actually very similar to conventional black steel rebar. You first, engineers need to design for safety, to make sure that the strength of a structure is adequate to withstand any foreseeable loads that may act on the structure. Then one would check for the serviceability to make sure that the deflections and cracks are all within a tolerable limit. And as I mentioned earlier in my presentation, GFRP bars are linear, elastic up to failure with no yield plateau. And for this reason, the fee factors and code checks are all calibrated now from the concept of deformability. And deformability is essentially the ability of a member to sustain very large displacement or deformations before failure. And based on our experience at MST Bar, when you design the GFRP rebars, serviceability requirements typically govern the design, not the safety requirements. So one of the challenges engineers faced when using GFRP bars was the lack of reliable design software. And to address this, we collaborated with Altair's team, and they have now integrated the ACI 440.11-22 code into Altair concrete design solutions. And from our experience at MST Bar, using this software has tremendously increased our workflow and efficiency in design. The process of our design, of our daily design tasks, and that was a very big step for this industry. And this brings me to the end of my presentation. Now I will pass it to Matthew to do his part of the presentation.
Thank you, Alireza. Let me just share my screen. Give me 1 second. All right. So I wanted to start by perhaps introducing Altair, since I see a lot of new faces in the audience that may not necessarily know the history of Altair and some of the concrete design solutions that we offer. So first of all, Altair at a glance. We have a large number of engineers, around, I think it's over 4,000 engineers now, spread out around the world, working on a variety of different applications for a number of different industries. So we have presence around the world, as you can see from this map here. And we look at the overall customer base. It covers pretty much everything from the engineers and designers that would design the car that you might have drove to the office today, to the engineers that design the building that your office might be in, or even the shoes that that you're wearing today, or the phone you're using. When we focus it more on what I'll call the S-Frame suite of products, that covers traditional structural engineers, I would say, working in the AEC industry. And that's actually where my background came from. I worked for S-Frame Software. We were acquired by Altair about 3 years ago, and we've been working with them ever since. And during this time of the acquisition, we started to work with MST Bars to develop some of the ACI 440 code implementation in our concrete design solutions. And those have been part of our code-based analysis and design solutions that you can see here, kind of at the top of this wheel of solutions that Altair offers to engineers. Now, we have other solutions for everything from optimization to blast simulation to CFD. So if you do work in other fields, there may be other solutions that could work for you as well. But I wanted to give you a bit of an introduction to what the S-Frame suite of tools do as well. And this really covers a couple different bases of structural analysis and design. So obviously structural analysis is kind of at the front and center there. But a lot of our clients will use our concrete design solutions, which cover the solutions that I'm going to be talking about today, even if they might be using a third-party analysis solver. Same goes for our steel design, our timber design, intersection calculations. Those are all available as a suite that you can purchase, and they interface with the outside world, as you can see. So you don't necessarily have to be stuck into one specific workflow. And our tools have been used for structures all around the world. I just showcased a few here. They're not necessarily all concrete, but I am getting to that. So we actually published a recent customer story on the Mumbai airport. This is a steel structure. You can see it's a very unique structure. We get into timber as well. This is one that's fairly near to me in Vancouver, Canada. Concrete structures as well, something that we offer not only the analysis for, but the design checks as well, from tall buildings to non-building structures, depending on what it is that you need to do. And the whole journey for us to support the GFRP Reinforced Concrete design codes in our software really started with our continuous concrete beam design software, which I'll refer to as S-Line. So this is effectively an integrated finite element analysis for serviceability and ultimate limit states. and it has a variety of different support conditions that you can use to represent either cantilevered beams or pins or column or wall sections above your or below your beam. And it does deflection design and code checks based off of the code-based effective inertia with considerations for things like cracking and creep. You can look at design forces at the faces of supports. Code-based moment redistribution is also considered. And ultimately, what you're getting out of this is member design and reinforcement layouts and reports that document all that as well. So you're getting complete design and a code check along the span of the beam, accounting for reinforcement layouts, splicing, moment, and shear and torsion envelopes. And those reports that I mentioned earlier, they also include the full code details for all the controlling loads for each span of your beam. And it could be a simple supported beam, like you'll see in the next example, or it could be a multi-span beam like you see here. So I'm actually going to jump into the recording here that I've produced ahead of time, just to keep things nice and succinct. So this is an example of a simply supported beam using S-line. And in this example, we're actually using the ACI 440 code, as you can see. On the right-hand side, we have the field to enter our material properties for the GFRP main bars and the stirrups. And what I'm going to start off by doing is setting up some reinforcing styles. So this just initializes the rebar layouts. We can obviously modify this afterwards, but it gives us kind of a high-level direction for our reinforcement. We can then apply our loads and any other parameters that we need to represent our beam and run an analysis and a code check. So S-line has an analysis engine in it to perform the analysis and then get the code check results from the demand capacity ratios. And that's what we see at the bottom of the screen, but I can actually drill down into additional results like my deflection diagrams. So for this simply supported beam, supported by 2 girders, and we can look at the deflection diagrams, moment diagrams, and I can get the actual numerical values at any single point I might be interested in. We can also see the capacity envelopes for shear and torsion on either top and bottom side of these diagrams. And if I want to look a little bit deeper into the results, I can look at the design report. And this is produced, in this case here, just for a single beam, but I can do the same thing for multi-beam spans as well. And it's going to highlight all the different design checks that were performed, any violations, along with clause references to the design code I'm using. So it gives me a very clear and transparent way of documenting this information. And I can quickly and easily change this design. So if I needed to add more stirrups to a specific area, I can just left click to add more stirrups. I can drag my steel to extend it into the beam, however I like. Now this is a more advanced example. You can see I have some cantilevers, I have some walls supporting this as well. And again, I'm using the ACI 440 code, showing where we can enter the different parameters to represent our material properties for this particular design. And I'm going to go ahead and once again run an analysis and a code check since my loading is already defined with automatic pattern loading and so on. And you can see these high-level results at the bottom of the screen. So it's showing me I have about 95% of my negative moment capacity being utilized. The same thing, about 99% of my shear capacity. Now, to get a better understanding for where these results are coming from, I can look at the analytical model that's used to formulate this. I can also look at things like deflections throughout my beam, either short or long-term deflections. So here I can toggle that on to look at that deflections with the effects of creep and cracking and their related moments of inertia. Here are my moment diagrams that are showing not only the moment redistribution, but the moments going into my supports, my shear forces. And lastly, we have our torsional diagrams as well. This is available, again, for the entire structure or beam system that we're working with. Just like before, I still have my access to my design reports. So all these warnings that I can see in my report, I can quickly drill down to and understand for any one of these beam spans where that might be violating the design codes. And in this scenario here, we can see we have a stirrup spacing section of a report where we have a warning. We also have skin reinforcement that a warning has appeared. And these are all listed at the bottom of the screen, again, accompanied by the clause references pointing to ACI 440. Now, one last handy feature that I want to highlight here is the ability to quickly compare different design codes and also reinforcing materials within your design. So this is an example where I'm starting off with a simply supported beam using the ACI 318.19 code. And I'm just looking at the moment capacity, in this case, in the negative side, which I'm getting a 925 kip-foot bending capacity at midspan. And then I can quickly go in and I can change the design code that we're using. which will inherit the rebar sizes that correspond to the GFRP rebar. I'm going to reanalyze. I'm not going to change anything else, so this may not be a totally realistic scenario. We're going to keep everything else the same. But then I'll be able to quickly compare almost side by side the moment capacity in this case. And I can see that for this example, the bending capacity has actually shot up quite a bit due to the strengths of the GFRP. Now, it may not necessarily always be a case that will favor GFRP. There are applications where one might be preferred over the other, but it allows us to make that comparison really quickly and help us guide ourselves along the design process. We've also implemented GFRP rebar design into our foundation design software as Foundation. And this can be used for deep and shallow foundations, and it can be allowing you to design your foundations as either a standalone workflow where you define your foundations directly within the software and apply your loads manually. You can also integrate your software that you use for your analysis, if it's ETAB, STAD, or SRAM, or if you just have a CSV file with all the foundation support locations, the reaction loads, that can be brought in as well. So it can be fairly agnostic in terms of where the data came from. And it's going to allow you to do structural and geotechnical design checks according to not only the ACI 440 code, but also ACI 31819, Canadian codes, and the European codes. It has automated design capabilities within it. And a cool part about S Foundation is that it actually has a built-in Python scripting interface that allows you to tap into the API of the software. So if you are the type that wants to perhaps stretch your legs a little bit more and modify the software or customize it to work with the way you want it to, this is certainly a way that you could interact in such a way. So I've got another example that I want to share with you. And this one here is of a spread footing design in S Foundation, where I've deliberately modeled an undersized foundation, at least according to the size of the loads that I have. So 1.2 meters square, essentially. And I've got a pedestal on top of that. I've got some default reinforcement, which is currently set up as steel reinforcement. And we're going to look at how we can actually perform a code check and define different properties as well for this. So I'm going to start off by looking at the load combinations and the demands on my foundation. As you can see, I've got two different load combinations. I've got a serviceability load combination with 1,500 kilonewtons of compression. And I've got a ULS load combination as well, where I've defined a sustained service load factor, which is just a sustained portion of the design load for GFRP creep rupture checks. And I've got a higher reaction load there as well. Now, as I mentioned earlier, this model has been set up with steel reinforcement. So I'm actually going to remove this reinforcement. And I'm just going to clear that out and load up our GFRP rebar database, which you can obviously modify to your heart's content as well if you'd like to. And it's going to inherit those new GFRP rebar. And I'm also going to change the concrete code that's being used from ACI 31819, and I'm going to switch to ACI 440.11.2022. So with this, I can go ahead and run an analysis and a code check. And I should just preempt this by saying that we've deliberately undersized this foundation. So you can see the utilization ratio or demand capacity ratio is very high. I'm using 12% of my, or 12 times my capacity. So we can see it's failing primarily due to creep rupture, but there is a lot of other failing code checks. And this was originally just set up to be kind of a garbage starting point that I'm going to iterate on to design. And we can use some of S Foundation's design functionality to accomplish this. So right now I have a 1200 millimeter square pad, 250 millimeters thick, and I'm using 6 number 2 GFRP bars in each direction. So it's really not designed in an intelligent way at this point, but we're going to get to that step. So I'm going to run through these design wizards that allow the software to iteratively come up with a solution, starting with the sizing of the pad to soil bearing. So I can set up my width and depth increments and basically let the software do the hard work of iterating to find a solution. And we can always fine tune it afterwards. So you can see here, it's growing that pad size until it finds a solution that is passing that soil bearing check. So now it's 2,300 millimeters squared. Before it was 1,200 millimeters squared. So it had to increase a fair amount. We can do the same thing for our pedestals as well. Our pedestals, again, have been deliberately undersized to kind of showcase this workflow. And you can see here, now we're getting a passing code check where we get 94% utilization, which is still pretty high. We can modify it again still from here. Now I'm going to look at bunching shear where I might want to increment the pad depth. to match the demands on punching shear. So I want to increase that capacity. And you can see that this capacity is increasing as we increase in depth. So I'm getting about 88% of my utilization now with that punching shear in a new depth. And finally, I'll look at designing the pads to flexure. So this allows us to basically change the rebar spacing within our pad in order to meet the flexural demands. And you can see here, without having changed the bar size, which I can now do as well, we can get to a satisfactory utilization ratio. So when I perform the code check for everything, I'll now have a satisfactory design that is passing all these code checks. And if we wanted to, we could then further modify it. But we can see the utilization ratios are much lower. And any one of these code checks, we can really drill down into and see the results, see why it might be highly utilized or not highly utilized, and understand the clause references and the factors that were used in coming up with these results. We also support foundations supported on piles. So if you do have a pile supported foundation, like the one you can see here, you can control the pile configuration, how many piles you have, how they're spaced, whether or not they're battered. I'm just going to go with 5 piles supporting this pile cap, and we have a mixture of compressive loads and lateral load that I'm going to apply in this scenario. So here I can go into the pad pile caps, or the soil profiles rather, and I can define my soil springs that represent the nonlinear ground springs that characterize the stiffness of the soil along the length of my piles. And I can go ahead and run an analysis and code check. And so this is showing me basically the axial force utilizations for my pile. I can look at deflections, and I can see deflections or forces within my pile members. So I can look at, for example, the bending moment diagrams. I can control things like the pile head fixity, so it might be pinned or it might be fixed. I can change the embedment length as well. And we can really get a lot of useful information to help guide our design process for these piles. And like I mentioned earlier in the slides, we may not necessarily always want to work with kind of a standalone workflow. If we've already got a superstructure that is analyzed and modeled in another application, we can import that superstructure and its reaction loads at the support locations and be able to perform design checks on that. So that's what we did here. We designed these foundations with the superstructure coming in from ETABS and ran the analysis and code check of the foundations with those forces coming in as well. So you can see here all the forces that were imported, and we had both SLS and ULS load combinations that we could use for both geotechnical and structural checks and design our foundations accordingly. And the last topic that I want to bring up on this webinar is concrete section design. Now, if you have used concrete, or if you have used Altair's tools for concrete design, chances are you are aware of concrete as well. And this is the last tool that we're working on to implement the GFRP codes. So this is coming very soon. And essentially what concrete allows you to do is it allows you to perform both code checks and design for reinforced concrete sections, those being beams, walls, columns. And it supports at the moment ACI 318.19 and older codes, CSA 19 and older codes, and in the ECA 2 codes as well. As I mentioned, the ACI 440 11/2022 code is coming. And this is a really powerful tool for processing a large amount of data for concrete design. And it's actually integrated with a workflow that can work with ETABS and SRAM and more tools as well, where you basically import your analysis data and use the concrete design engine to set up a preliminary design reinforcement, fine-tune your design, and come up with design sections with reinforcement data and design reports for all of your reinforced concrete sections. This can be obviously run in batch to handle a large amount of data. So it covers everything from the design of the main rebars to the stirrups, looking at things like anchorage checks and ductility checks as well. So this is another quick kind of intro to concrete. Right now I'm looking at just a beam section for this example, and I can see the reinforcement and the loads that have been specified. So these loads, they can be imported from other applications like I mentioned, or they can be just entered into this spreadsheet. And these are all assumed to be factored loads on our section. And I know right now that my section is overutilized due to axial load and moment, so I can set up my own design constraints to perform an automated design. So I might want to freeze certain parameters and let the software adjust the reinforcement, for example. And that's what I'm doing here. I'm saying basically maintain the section size, but adjust the reinforcement within the section. And it's come up with a section by adjusting the reinforcement that's being used. And it's found that 4 number 11 bars on the top and 5 on the bottom were satisfactory. We can also design columns like I mentioned. So this is an example here where, again, we have an overutilized column. And I can actually manually change the design very quickly just using these hotkeys. So I can left click on the number of bars or the size of bar, and it'll increase that bar size, and instantaneously I get feedback on that design to verify that it's meeting the code criteria or not, so I can see what effect that might have had. I can also stretch out the section if my design allows me to, and see those results very clearly. And just like we saw in S-Line as well, we get a nice, concise engineering design report that's showing us all the code violations, the reasons why we might be failing or passing our design checks. That's all documented very neatly for us. As for walls, again, we have similar control. Walls add a few extra elements to this design. So in this scenario here, I'm looking at a shear wall that has both zone and panel reinforcement, which can be controlled independently of one another. I can also look at my loading being applied as a cross-sectional load or as a panel-by-panel load basis. I can get my interaction diagram so I can see my, my failure envelopes throughout this section. And what we foresee this being useful for is being able to quickly compare those sections and design codes, again, very quickly, and see where our strengths and weaknesses of each material and each design methodology might favor our particular application. So this allows you to design both for black steel and GFRP reinforcement and be able to utilize and recognize the strengths of each material for the proper applications. So hopefully from this presentation, you've been able to see that we are able to perform design checks on GFRP reinforced concrete for customizable geometry and loading. There's also very powerful analysis built into the tools that we showed earlier, like the S-Line analysis and S-Foundation, that'll facilitate the code checking process as well. And these tools allow for quick optimization of the design, not only for you allowing yourself to be able to study very quickly different materials and design codes, but also being able to look at different configurations of GFRP reinforcement or even black steel reinforcement if that's the direction you decide to take. And we don't want to be a black box. We do our best to output detailed and transparent design reports, and I think that's something that our clients really value out of the software. And as of now, we also support the GFRP reinforcing concrete design with the ACI 440 11/2022 code. So at this point, I'd like to open up the floor for questions. I'm just going to mute my line for a second here while we read out the questions. And again, if you do have any questions, there is a Q&A pane that you can type those into. Whatever we can't get to, again, we'll respond to in the coming days via email. So I'm just going to mute my line here while I read a couple of the questions, and both Ali Reza and myself will be happy to answer those.